Okay, guys, let's talk about Diophantine equation and convergence of parameter adaptation algorithms. Here is what we arrived at from last time. We noted this polynomial equation is closely connected to the hyperstability result, while the adaptation error converges to 0 means this polynomial equation operated on the input signal will go to 0. And obviously, trivial solution, which is the solution that we want, is A hat equal to A and B equal to B hat. All right? Another possibility, as you can imagine, is all of these are 0. Like A hat, B hat, this is 0, right? Which is making this entire thing multiplied together to be 0, which is not very interesting to look at. We want to look at the case where the coefficients of these unknown polynomials are not 0 and will converge to the true values. So today we're going to take a look at the scenario. Let's do some operation on this equation first to make the result a little bit easier to look at. The first thing that we can notice is we can do some add and subtract items again to arrive at an equation that is dependent upon the difference between the actual parameter and the estimated parameter. So if we introduce A tilde to be A hat minus A, ideally we want this to be 0 is our goal. All right? So we can arrive at this equivalent. These two are equivalent. We can arrive from here to here by add and subtract items. All right? So if we add and subtract this AB polynomial multiplication here, then you can see that we're going to have A hat using the negative portion of the added term. We're going to have A hat minus A times B. Right? There's a common term about B. Then I have A hat minus A plus A. Then I'm going to use this plus portion. I will have A times B minus B hat. Right? So A, B minus B hat. And then we can arrive at this new version with representations from the difference between the true and the estimate polynomials. And then let's consider this whole thing. After you multiply things out, it's going to be a new polynomial. Let's say this polynomial is alpha. Coefficients are alpha 0, alpha 1, alpha 2, etc. This whole thing is going to be a Diophantine equation. So A tilde B minus A B tilde equal to this alpha polynomial is a Diophantine equation. Then we can use our conclusions from last time to tell about the solution concept. We know from last time a Diophantine equation has a solution, has a non-zero solution under the condition that the known polynomials A and B, if they are co-prime, then we will be able to find guaranteed solutions for these unknowns, A tilde and B tilde. In our setup, we have, these are from our plant, right? So these two co-prime, they don't have common roots. So therefore, the Diophantine equation has a unique non-zero solution. Has the structure, let's do this. All right, so last time we transform this polynomial equation into this matrix equation, a big matrix times a vector equal to another vector, has this type of structure. And we know if they are co-prime, then this is going to lead us to a non-singular or invertible, let's call this S matrix. So that's the result from last time. This matrix is actually have a special name. People call this Sylvester matrix. Sylvester matrix. So we know this is invertible if these two are co-prime. So therefore, we know from here, we want, again, let's go one step back. What do we want, right? We want this alpha polynomial to be 0. In that case, A tilde, B tilde, A hat equals to A, converges to A. And if this co-prime condition is satisfied, we know that the goal is to do this. This is our goal, right? And we see the only possibility under this co-prime condition is indeed these A tilde, B tilde polynomials. It's indeed, if you look at this, so if this is invertible and the right-hand side is 0, then the only possible way for this vector is to be 0, right? So this is coming from the alpha polynomial, right? And these elements from this vector comes from A tilde and B tilde. All right? So therefore, we see, indeed, the scenario that we will be able to make sure if this is 0, then we can indeed claim that A tilde and B tilde, these polynomials, have 0 coefficients, which is what we want. All right? So the first condition is therefore A and B, they need to be co-prime. This is the condition. Transfer function needs to be irreducible. All right, so that's the first condition. Now that is cleared out. All right, we know if we want to have correct convergence, we need to make this to be 0. Now, the other piece of information that we also talked about is I don't really have alpha Q inverse to be 0 from this condition, right? So what we have is this alpha operating on U gives us 0. And that is not guaranteed to give us alpha to be 0. All right, we had an example last time. Let me give you another example. So let's say U is a sine and cosine signal, omega, which is very common in reality. Let's say if alpha is 1 minus 2 cosine omega Q inverse plus Q negative 2, you can show that under this setup, alpha operating on U will give us 0. We have a non-zero polynomial operating on non-zero signal, and the output is 0. And it's not difficult to show. You can You can check by looking at UK. Cosine signal is half of, let's use the Euler equation. This is our cosine omega k. And then alpha Q inverse. This one is actually, so I designed this actually on purpose. You will see why, how this design actually works. All right, so let's check. Alpha is really these two multiplied together. You can check by looking at the product j omega e negative j omega. There should be Q inverse here, Q inverse here, then Q inverse, Q inverse, then here is Q negative 2. Okay? So you can see that this is really the case. This is 1 minus e j omega plus e negative j omega Q inverse plus Q negative 2. And then this is 2 cosine omega k omega from the Euler equation. These two are all connected very closely by the exponential signal. So if we use these exponential expressions, we can see that alpha operating on UK is nothing but 1 minus e j omega Q inverse 1 minus e negative j omega Q inverse. And then operating on half of e j omega k minus plus e negative j omega k. I would like you to spend some time and show me that this is 0 after you multiply things out. Okay, so spend some time on this and then go back to the starting point and see that the impact, the relevance of this analysis. The computation is straightforward, but I think the insight is very important. You have a non-zero polynomial, you have a non-zero signal, but you can generate an output of 0. This is actually a very important result in any kind of digital filter design. All right? If you have, for example, a high-frequency noise, you can filter it out with a low-pass filter. This is the same concept here. This type of filter will actually remove the frequency component at a single frequency. And another insight is this. This is if I have only just one frequency component and my system order is 2. Okay? So for second order polynomial of alpha, it is possible to make the output to be 0 by inputting a single frequency component. Now you can try if you increase the complexity of your input, then your filter will no longer be able to handle it. All right? If you increase the complexity, if you double the complexity, 2 frequency components, one at omega 1, another at omega 2, and omega 1, omega 2 are not different, are different. So you have 2 independent frequency components. Then you can't shut it down by a second order polynomial. Anyone know how many orders I need to use if this is 2 frequency components? 4. Yes, that's exactly the result. You must have looked at here. Anyhow, that's a good guess. So it is, you can do this again here and see that if your frequency is increased and you still have the same order, you still keep the same order, then the only way for this to be 0 is all the coefficients must be 0. That is actually a good result for us. That is saying you want parameter convergence. You want your alpha to be 0, right? How can we make sure this kind of condition is satisfied? Make your input to be rich in frequency components. All right? This is called persistent excitation condition. You don't have to copy this down. This is on the notes. It is also called frequency richness condition for PAA convergence. It is basically saying it gives you a bound that you must, a minimum number of frequency components that you need to give to the system to make the convergence happen. There are some numbers that this fact tells you. Choose your input to be at least containing these independent frequency components. Then if you still have the irreducibility of the transfer function, which is what we talked about at the beginning, then you're going to have convergence. The estimated parameter will converge to the true parameter for the series parallel predictor PAAs. That is the overall concept. And then let's dig into the numbers a little bit. The numbers are here, right? If n is the order of A, m is the order of B. So depending on whether you combine them together, whether the result is even or odd, you can have slightly different numbers in here. So in our example here, we can see, so alpha, if alpha is a second order, right? So if alpha is a second order here, then that means A and B, let's look at this. If alpha is a second order here, that means A and B, they are at most first order, right? So first order times first order gives the second order. So in this case, n and m are, in this example, let's say n and m are 1. Let's check the conditions. N plus m is going to be even. So the minimum amount of frequency components is 1 plus 1 divided by 2. So it's 1 here. So it's 1 plus 1. We need 2 independent frequency components, right? This is only 1. So that's why it's failing us. So this is convergence. And this is for series parallel predictor only. All right, we're going to talk about parallel predictors later. Before we talk about the parallel predictors, let's go back and think, why did we use the parallel predictor? We said we use that because it's more robust to noises, right? So let's think about the noise impact first. Let's use a block diagram. This is the block diagram for series parallel predictors. So this is equivalently A operating on Y equals B operating on U plus W. All right? Without this W term, this is precisely the previous way of system modeling. Now we just have a noise term. We can write it using the regressor vector 2. Okay, so it can be written as a regressor vector, regressor form 2, looking like this. So we have the noise term standing out. If this is the system model, then in the prediction, let's say y hat, right? The a posteriori prediction that we did in the past is this. Okay? Because we don't know, if we know nothing about the noise term, then if this is a white noise that's independent from input, then the best thing is to do this prediction. Okay? If this is zero mean, all right? Then the best way we can do is to do this. So let's take a look at the a posteriori estimation error. Okay? It's going to be y minus y hat. And it's going to equal to relatively straightforward computation. Theta minus theta hat, all right, is theta tilde, negative theta tilde based on our definitions. And then there's a noise term. So our parameter adaptation is built upon this formula. Right? So the adaptation error is going to go through this integration and drive this theta hat update. And the noise impact, if we be explicit, is going to become, let's call this epsilon under bar, k plus 1, a prediction error without the noise. Let's call it this way. Then substitute inside, the result is going to be this. All right? So some obvious, some trivial write-up, but in the end result is we have this noise impact coming in this way. So F is the adaptation gain, the regressor vector, times this noise term. And the indices are important here as well. K, these are all information up to time K. and this is information at k plus 1. And then this part is the noise-free, previously appeared version of the adaptation formula. So the result is that think of this as this is type of one form of integration. I mentioned it earlier as well. So if you're adding information, keep adding information as k improves, then this effect is sort of like a integration effort. We can't make this to be 0. All right, this is a noise term. And these elements inside, these are not 0 either, always, right? However, we can consider the scenario in a statistical way, all right? So in a statistical sense, if you keep adding some signal together, if on average they cancel out, then it is still okay, all right? If you, in the previous time instant, you add -1, and the next time you add 1, and then you keep jumping around, if on average it's 0, then it is still fine. So if, from a statistic stance, we can still have convergence if on average the expected value of phi epsilon or w is 0. So that is the good news in a way. This is on this side. And then be also mindful about this term a little bit. Even if this on average is very tiny, if this is a huge number, then things still will be troublesome. All right? So the second piece of information is if this is on average 0 and fk will in the end go to 0. All right? Then we should be fine. All right. So let's tackle the easy case first. This is very easy to satisfy because remember how we update our adaptation gain is lambda f inverse plus lambda 2 phi and phi transpose. All right. So f inverse keeps increasing. If f inverse keeps increasing, then f will keep reducing. Right? So we need to make sure, need lambda 1k to be converging to 1 and lambda 2k to be less than 2, larger than 0. All right? So if this portion keeps adding, then you're going to keep increasing f inverse. Then in the meantime, this is sort of like an integration again. You can't have lambda 1k to be, for example, less than 1. Or if you want to be extreme, you can't have lambda 1k to be 0. Because in that scenario, you're not adding. Okay? So you need this to be converging to 1. So that's easy. This is quite easy to do. The second piece here, this is sometimes easy, sometimes not. All right, so let's work on this a little bit more carefully. Let's recall in our series parallel PAA, our phi is constructed as negative yk minus 1, etc. uk minus 1. So let's take a look at how individual signals, if they multiply together with W, what kind of information will be obtained. U is a deterministic signal, is what we compute. All right? So expected value of UK, WK plus 1, this is actually 0. All right? This is what we compute. If this is a zero mean signal, then this whole thing is zero mean. This one, I will be more specific. If WK plus 1 is zero mean, independent from UK, okay? Product here, Y contains information about the noise from the block diagram over there, right? So Y actually is a stochastic signal. It contains noise information in here. So if this is contains noise and this is another noise signal, these two statistic signal multiplied together is not necessarily zero mean. In the most ideal scenario, if W is white, it's a white noise, then we can have the good results. If this is a white noise, and then the time index, this happens after YK, then we will be able to have the expected value to be 0. Okay? So if these two are independent from each other, then we can have the expected value to be 0. These are the conditions here, right? Two conditions to make the convergence to be unbiased. Now, in reality, though, we are not usually getting W to be zero mean and white. Okay, so in reality, this is more often than the first block diagram that we drew. Usually, we use some kind of sensors to measure the output. Inertial sensor, encoder, etc. Usually, the noise, there will be some measurement noise that is usually white. If you go to a data sheet, spec sheet, then you will see this can potentially be a white noise in the measurements. And that happens because of different scenarios. If it's a digital measurement, then there are quantizations happening to generate the measurement. Then something called quantization error will appear that is usually white. All right, so in this kind of scenario, I'm going to use N here. Okay, so N can be white. Let's see what is the equivalent W signal in this block diagram. So the signal relationships are YK plus 1 equals B A UK plus this noise term. This is the output error type of structure. So this is equivalent to A Y equal to B U plus A N. So this block diagram has this type of realization. And if we compare with the WK equation on the right-hand side, you will see that this is the equivalent WK plus 1 signal. So this example shows you that even if you have white measurement noise NK, then it can actually generate a WK that is a white noise filtering through some kind of filters. And the result is that this cannot be white anymore. All right, so okay, so that is why the series parallel predictor kind of structure is challenged in reality. Okay, so your noise will actually impact your parameter convergence if you use a series parallel predictor that has this type of phi structure inside. All right? Now, I will give you the good news, though. In parallel predictor, however, phi is using this, the computed signal. So in the parallel predictor case, the regressive vector is actually using computed estimated output instead of the true output. Okay? So this is deterministic. This is what we compute. So therefore, if we do again expected value of this, it is much, much better than doing the expected value of this. Okay? So it's still quite promising that you're going to get a zero mean output. So that is why now we can go back to the storyline, why parallel PAA will give you better convergence if there is noise. So we're going to talk about this a little bit more next time.